Hello, everybody. In this session, we're going to kick off this operating systems course by doing an introduction to operating systems. So we'll endeavor to answer the question, well, what is an operating system? We'll look at the general organization and the roles of an operating system. But ask the question of why study operating systems, because none of us are probably ever going to actually write the code to design an operating system. But there are reasons why understanding how operating systems work are really important. We'll look at computer system organization, so how computer systems are organized. We'll go through a general overview of computer system architecture, and you folks have all been with me through the computer architectures course, so you already have pretty good grasp of computer system architecture concepts. But first, let's answer the question of, well, what is an operating system? Well, the definition, an operating system is software that manages a computer's hardware. So it acts as an intermediary, so like a middle person between the computer user and the computer hardware. So it kind of intermediates between the two when they need to interact. And there's various reasons for the software needing to interact with the hardware. For example, you may need to print your Word document that you've been creating. Now, operating systems are everywhere. So we have these days, we all probably have smartphone devices. I'd be very surprised if any of you didn't. We have computers, laptops, desktops. We have cars that have onboard computers. We have appliances. And we have these days, which is becoming more and more popular, is the Internet of Things, or IoT. Lots of IoT devices that allow us to interact with appliances, for example. And an operating system has at its disposal or at its use CPU. It has memory, input-output devices such as keyboards, mouse, trackpad, touchscreen, and storage devices. So different ways of storing information. Magnetic disks, traditionally, solid-state drives, etc. So all of this makes up an operating system. And an operating system must be able to allocate resources efficiently to programs. So programs need to run. And so the operating system helps those programs to run efficiently and to not step on each other's toes, so to speak. So from the user's view, we'll take a look at that first. The user's view is designed mostly for ease of use. So users these days, of course, want an operating system that allows them easy access to all of the applications that they're used to using. So most of us spend a lot of our time with computer systems interacting with our smartphones, and it's becoming more and more prominent. There was a time before smartphones where most of our time would have been spent on laptops. I'm a little bit of the older generation, so I actually prefer more time on my laptop. I'm more productive using laptop than I am smartphone. And so we want the user to be able to access their application programs very easily. So application programs such as compilers if we're writing code, so PyCharm, our web browsers, so Chrome, Safari, Edge, and then development kits, etc. So any application that we're used to running, and for us who use our smartphones to communicate, of course, all kinds of different social media applications. And so the application programs are basically on a layer above what we would call the operating system, right? And so if you're running, if you have an iPhone, you're probably running your iPhone on a version of an operating system called iOS. I have an older iPhone, so I'm on an older version of the iOS. If you're using a Samsung device, any type of non-Apple device, you're probably on an operating system called Android, which is managed by Google. And so even on your smartphones, depending which one you're on, that operating system is the intermediary between the applications and the computer hardware. So for example, if you're going on to a social media application, Instagram, for example, and you want to post a picture, that Instagram application, I'm assuming most of you access it through an application and not through a web browser, but in either case, that application is going to go through the operating system, whether it be iOS or Android, to the computer hardware to access that picture, which is stored there, right? So the operating system handles that transaction between the application and the computer hardware. So it allows you to embed your image into Instagram so that your friends can see it over the internet. So the user view is designed mostly for ease of use. And there is some attention paid to performance, of course. The users want their applications to run smoothly. And then security. So some way in which there's secure access to the operating system and then secure access within the operating system. So that, for example, user programs don't tread on system processes. Now, as I'm talking here, of course, I'm talking about how users increasingly use smartphone and tablet devices. So the way in which these applications interact through the operating system hardware is becoming, a much more researched area, I guess is the way to say it. And these devices are connected via cellular and via wireless. Of course, cellular if you're not near wireless, but wireless if you're in, a restaurant or other public area. So that's the user view. The other view then is the system view. So from a system view, the operating system is the program most intimately involved with the hardware. So if you're programming at the system view, you're not as much worried about the OS to the application, you're more worried about the OS to the hardware. So a little bit what we would call lower level. And so from a system perspective, the operating system is a resource allocator. So it decides which applications have access to which resources. So it manages CPU time, it manages memory access, it manages input and output devices and any other stuff related to hardware. So a slightly different view is that an operating system then is a control program, right? It controls accesses, it controls who has access to what. So it manages the execution of user programs to prevent errors and improper use. So again, we want the user programs to be separated from the system programs so that we have to have a way of managing whether users have access to system resources or whether system processes have access to system resources. And part of this course is figuring out how to do that programmatically. So the term operating system, as you can probably tell by now, covers many roles and many functions. So a myriad of designs and uses for computers, myriad meaning a lot. So there's a lot of different designs and a lot of different uses for computers. And this whole smartphone revolution has really changed kind of the focus of where research and development is taking place. Back 15, 20 years ago, before smartphones, it was all in kind of laptop, desktop environments with mouse and keyboard. And nowadays it's smartphones with touchscreen and voice as an example. So the bottom line, there's no universal definition of an operating system. So generally we say that operating system is the one program running at all times on a computer. So when you start up your laptop, that system will look immediately for where the operating system is and which operating system to load. Same thing with your smartphone. When you turn your smartphone on, it goes through a boot up process where one of the early things it does is find the operating system and then load the operating system. So that happens seamlessly without us having to do any intervention. And so the operating system itself then, without any user intervention, without thinking about the high-level applications, the area of the operating system that runs all times is the kernel, right? So even if you have no applications open, when you turn on your device, the kernel is running, right? So the kernel is running and it's ready to go to start handling any system processes that need to be undertaken. For example, as soon as the user starts typing, then the kernel will start to handle all of the keystrokes that are coming in from that keyboard device or touchscreen or whichever way we access our applications. So this is basically just what I've been saying here, right? It works with the system programs and the applications. So why study operating systems? Well, few people will actually create a new operating system, right? But almost all code runs on top of an operating system. So understanding how operating systems work helps us become better at writing code that goes on top of an operating system, for example, an application, right? So understanding how operating systems work is essential to efficient, effective, and secure programming. So if you're writing an application needs to, for example, save users' information to a storage location. Understanding how operating systems work lets you program that much more easily, using an API, for example. So computer system organization, modern systems consist of CPUs and device controllers connected through a bus. So we have CPUs, disk controller, USB controller as an example. So USB controller might handle multiple devices, a mouse, a keyboard, a printer. We have some sort of a monitor with a graphics adapter. Graphics adapters have become very advanced over time. And then you can see the system bus connects them all, for example, to memory. So modern systems are all connected through a bus. Now, operating systems have what are called a device driver for each device controller. So we'll talk in much more detail as we go forward about what device drivers are and how they work. But they're basically an intermediary between a device and the operating system. So they kind of make it easy to interact with that device without having to do any extra configuration. So access to devices in an operating system is handled by what are called interrupts. We're going to talk in great detail about interrupts. Device controllers manage devices using device drivers, and they raise interrupts. So if you hit a stroke on a keyboard, that will be handled as an interrupt. So if we press a key, that needs to be processed, that keystroke. Okay, and so by creating an interrupt, then the CPU the keystroke is given access to the CPU, so that can be processed and then, for example, displayed in the monitor for the user in a word processing program or whichever program they have open. Now, modern systems use a system of priorities. And efficient interrupt handling is required for good system performance. So all modern operating systems handle interrupts well. And we also have to be able to handle unrecoverable memory errors, and they use what are called non-maskable. So maskable interrupts versus non-maskable interrupts. And non-maskable interrupts are things like system errors. So there's been an error in the code that's running, and so we need to be able to handle that. So we might have a math error, a null interrupt, the breakpoint in our code, etc. So the operating system has to be able to handle that, and it handles that through what's called a non-maskable interrupt. Looking at the storage structure, so most modern systems provide a hierarchy of storage. And this is shown in I actually really like this diagram because it goes from over here, access time. So down here are the slowest access time storage, and up on the top here is the fastest access time for storage. Of course, as we learn in computer architecture, as we go from slower to faster, that's great, but there's an increase in cost, right? As we move into faster devices, faster storage types, they become much more expensive. And over here, so storage capacity then, taking cost into account, of course, we're going to have larger storage capacity for less expensive. So if we have, for example, data that we don't access on a daily, monthly, or even yearly basis, we might store that what we call tertiary storage in magnetic tapes or optical disks. And we might actually even store that information off-site somewhere. So that's tertiary storage. Hard disks and non-volatile memory. These days, there's kind of two. This traditional magnetic hard drive disks aren't as prominent anymore. We've moved more into what we call solid state drives, which have non-moving parts, so more reliable and also quicker. Then into the main memory, then cache. And remember, we talked about different types of cache, L1, L2, L3. And the faster the cache, the more expensive it gets, and then into our registers. So what we need to understand is that there's a hierarchy of storage, and how we manage that storage that can be managed by partly by our operating system. Yes. Input-output structure. So a large portion of OS code is dedicated to managing input and output. It's important for system reliability and performance to manage input and output. So high volumes of data can be moved using what's called DMA, and that's what we're showing in this diagram here. So over here, we may have a device, and rather than go through the CPU, as we see here, what direct memory access does is it allows us to move information directly into memory, offsetting some of the load on the CPU. So DMA is a very common concept, and we'll talk more about that going forward. And so again, this offsets some of the load on the CPU. So we've taken a full course on computer system architecture already. So quickly through kind of general computer architecture ideas. CPU, hardware that executes instructions, right? The core, the heart of a system. The processor is a physical chip that may contain one or more CPUs. These days, more than one CPU is common. The core is the basic computation unit of the CPU. And again, these days we use what are called multi-core, so multiple computing cores on the same CPU. Multiprocessor includes multiple processors. So these are all concepts that we should have a grasp of already. And virtually all systems these days are now what we call multi-core. Just looking at kind of what a modern system looks like. So this would be a modern desktop system, not a smartphone. The inside of your smartphone wouldn't look anything like this. So we have CPU, we have DRAM sockets, we have PCIe bus slots, we have input-output connectors. So this is what a typical kind of desktop system would look like today. So all of the components that make up a computer system. Clustered systems. Another type of multiprocessor system is the clustered system. And this generally consists of connected multi-core systems. And it provides a high level of redundancy. So in instances where we can't have any downtime, where we need to have 24/7 uptime, 365 days a year, we might want a clustered system to ensure that that is what actually occurs. And it's usually used to provide high availability. So it can also provide high performance computing as well. So two reasons to use clustered systems. All right, so that's all I wanted to talk about in this kind of overview of operating systems. So just to quickly summarize, talked about what an operating system is, the general organization and roles of an operating system. So we talked about the user view and the system view and how those are different, right? So applications for a user and more system processes from the system view. Why study operating systems? Because it allows us to become better at programming, for example, applications that run on an operating system. If we understand operating systems, we know how to interface with, for example, an API that allows us to save to a storage location. We talked about computer systems organization, a little bit about computer system architecture. All right, so thanks for listening to this first session in operating systems. Take care.